Hello. So in this video, we're going to look at displacement time graphs. Okay. Last time in the last chapter in mechanics, we looked at displacement. What it means, I guess, in simple terms. So let's say I have, let's say someone's here, right? Then let's say they walk, let's say 5 meters, and now they're there. Now, if I take that the positive direction, right? Let's say forwards is positive, then the distance, obviously they walk 5 meters, so the distance would be 5. But also the displacement would be 5 as well. Now instead, let's say the person walks backwards and walks the other way. Right, so they walk that way by 5 meters, right? Well, physically they still walked 5 meters, so the distance they travelled is still 5, but now they're in the negative direction. So again, this is the positive direction forwards. If they're going backwards, that's what the negative way, the other way. So the displacement will be -5. Okay. And so the idea is with displacement, it kind of attaches a direction to where people are walking in. So it's distance, but it also takes into account if they're going forwards or backwards or left or right or something like that. It incorporates direction as well as the physical distance they travelled, okay? Okay, so I want to imagine the scenario, just to set the scene. Let's say I walk to a shop. I walk to a shop, that's 100 meters, let's say, 100 meters, and it takes, let's say that takes 30 seconds, right? Very, very close shop nearby, right? Then I stay in the shop. I'll stay in the shop for let's say 20 seconds. I don't know, very quick trip, and then I'll return home. Then I return home in let's say 40 seconds. Okay. Okay, so how do I want to visualize this as a graph then? So again, let's say I have a home, right? That's home. And let's say the direction towards the shop, is positive, okay? So, how do I want to represent this as a graph? Displacement time graph. Now, what we're going to do is construct this graph here. So, on our axis, it's time, and then we have displacement. Okay, so it's displacement against time. And our units, again, units, the questions will specify, but obviously, as we looked at before, the SI, or sort of the standard units we use for time, is seconds, and for displacement is meters, okay? So, let's have a look. So, the first part is I walk to a shop from home, right, that's 100 meters in 30 seconds. So, let's say 100 meters is here. So then let's say, if I have this ruler here, this line, right, let's say that's 30 seconds, right? 30 seconds. So what that's saying is, I start at home, so at home the displacement is 0, because if I'm measuring from the home, obviously if you're at home, you're not travelled anywhere. So we start at 0 at home, and then at this point here, this is at the shop, okay? So the 100 meters means we've walked 100 meters, but more specifically, it's positive. The line is positive, right? the gradient is positive, the line is going up because it's the positive direction. If we could walk from the home to the shop, that's in the positive direction, so hence the line is positive. Okay, now what else we can work out, quite interestingly, not only can we work out or plot displacement and time, we can also work out the velocity at any point. Okay, so the velocity is the gradient of the curve. Okay, of the line, sorry, of the graph. So if we were to work out this line, this gradient, well, the gradient is changing y, changing x, if you will. Obviously we've got displacement and time in now here. Now the change in displacement is 100 meters, right? 100, and the time, well, it's just 30, right? From 0 to 30 seconds. Hence the gradient is going to be changing displacement. So changing displacement over changing time. Pretty much the same idea as changing y, changing x is sort of normal graphs, right? So the gradient of the line here, right, it's 100 over 30. Okay, or as a number 3.33. Okay, now that's the gradient, so that means the velocity will also be 3.33. Okay, so the velocity, if I get rid of this, the velocity is the same as the gradient here, which is 3.33 meters per second. Okay, now the next part, then it's talking about I stay in the shop for 20 seconds. So what that's going to look like if I stay in the shop, I've not really moved anywhere, I'm still in the shop. So what happens is we have a flat line. Okay, there. So let's say that's 20 seconds. So from 30 seconds to 50 seconds, right, that'd be 20 seconds. Now let me get rid of this. So I'm going to say that velocity, let me write it here, v for velocity is 3.33 meters per second. Okay, now this part of the line, that represents how long I'm in the shop for, right? So again, the second part of the journey is I stay in the shop for 20 seconds. Now it will remain at 100 meters because I'm still in the shop, right? I'm still in the shop, I've not moved anywhere really. Now, do not get confused with, oh, if it's still at 100 meters, I've walked 100 meters. That's not what that's saying. It's saying the displacement is the distance from the house, okay? If I'm still in the shop, and the shop is 100 meters from the house, if I'm still in the shop for all that time, I'm still 100 meters away from the house. Hence, it stays at 100, okay? So it's not that you walked 100 meters in that time, you just stayed 100 meters away from the house. Okay, that's a displacement. And then the velocity then, well, again, the velocity is the gradient, but the gradient is 0, right? The line is flat, it's completely flat. So that means the velocity will be 0, which makes sense because I'm not moved anywhere, right? So I'm still, effectively. So no velocity. Okay, now for the final part, we have I return home in 40 seconds. Okay, so after I leave the shop, so at this end point here, that's when I leave the shop. And then for the final part, if I extend my graph, there we are. So we have time here. So in 40 seconds, that would be, if I add 40 seconds onto 50, I get 90 seconds, okay? So then that would be 40. So what that final line is saying, I return back to 0, okay? The displacement returns back to 0 because I've returned back home. So the distance away from the house, if you return back home, is back to 0 meters. So it ends at 0, and then this point is where we leave the shop. This point is where we enter the shop. And so then we can see that here, and it's in 40 seconds, okay? So there we are. And then if we were to compute the gradient again, so the gradient, we're here. Well, the change in y, the change in displacement would not be positive 100. No, it would be negative 100, because displacement, it's going down. The line is going down, so the gradient would be negative. Okay, and that makes sense, because it makes sense for the displacement here in this final part of the graph here. It's going down by 100. It's negative 100, because as we discussed up here, the direction from the home to the shop is positive, but at this final part, what I'm saying is I'm going from the shop to the home. So the other way, which would be negative. So the displacement would be the negative distance, okay? So hence we get negative 100 meters there, right? And so as the time is 40, the velocity at this point is going to be changing displacement. Well, it's minus 100 for displacement over 40 for time. And then if I simplify that, I get minus 2.5. So minus 2.5 meters per second. And again, velocity can be negative as well. Velocity is speed, but again, it incorporates a direction. So how much are you speeding in which direction? Okay, so there we are. So that is the idea of a displacement time graph. Okay, and also to realise that the velocity is the gradient of the graph. Okay, so I hope you have a good rough idea about what, using this scenario, about what the displacement means on the graph. Okay, so in other words, if it's going up, it's going in the positive direction. If it's coming down at the end here, it's going in the other way, the negative direction. And then if it's still, then they've not moved anywhere. Okay, they've stood where they are. Okay, the final bit we need to look at is the idea about average. So average velocity firstly. Now average velocity, you might be familiar with distance, speed and time, and that distance and speed is distance over time. Well, velocity is kind of like speed, so instead of just distance, it's going to be displacement. So we want the total displacement over the total time. Okay, and what I mean by this is the average velocity throughout the whole journey. So obviously, if we can work out the individual velocity of each sort of line, each part of the journey, but let's say we want the overall average velocity. So we need the total, okay, from start to finish. Well, firstly, total displacement. As we discussed, so if we want the velocity for the whole journey on an average, we want the displacement. We want the displacement from the start, which is here, to the end here. Now actually, we start at 0 displacement and we end at 0, which again makes sense because we start at home and then we end at home, right? Well, because there's no difference in displacement, we've gone from 0 to 0, the total displacement is just 0, right? And then the total time, well, the time in total is 90 seconds, okay? Well, 0 over 90 is still 0. So the average velocity is 0 meters per second. Okay. Now, obviously you might be thinking, how does that make any sense? Because obviously he's moved throughout the journey, right? He's moved to the shop and he's moved from the shop to the home. How can the velocity be 0? It'd be like he stood still. Now that's measuring from the start to the end, where how far he is away from the house. But if he starts at the house and ends at the house, really there's no displacement changed. But what we can say instead is average speed. Okay, now average speed doesn't care about this direction. It just cares about physically how far you moved or how far you walked. Okay, so the speed is now the familiar formula you'll be used to: distance over time. So the total distance of the journey over total time. Now the distance is not displacement. Distance is just how far we walked. Doesn't matter if it's from the shop to the home or from the home to the shop. We just care about physically how far we walked, either way. So to work that out, well, the distance, we can just consider each individual part. So from the first part here, he walked 100 meters, right? So the distance is 100. Now, for the second part here, the flat part, he's not walked anywhere. He's been in the shop the whole time. So there's no distance travelled, he hasn't walked anywhere. But at this point here, he has walked from the shop to the home. Now the displacement would be negative 100 because obviously he's going the negative way from the shop to the home. But the distance, he still walked 100 metres, right? The distance still is 100. So the physical distance is 100. So we add on 100. And there we are. Over total time, again the time is still 90 overall. So that'd be 200 over 90. And then as a number, that would be 2.22 meters per second. Okay, and there we are. And so yeah, so this is what you need to be familiar with: velocity to do with gradient, and then you can work out the average velocity or speed by considering the total distance or displacement over the time. Okay, let's have a look at some examples then to demonstrate this. Okay, so we've got this example, and we're told a cyclist rides in a straight line for 20 minutes. She waits for half an hour, then returns in a straight line to a starting point in 15 minutes. So the first part of the journey in a straight line for 20 minutes, you can see that here. From zero to A, that's the first part in 20 minutes. And then she waits for half an hour, that's the second part. You can see that here. It's a completely flat line, which means she's not walked or moved anywhere. And then she returns to a starting point, and then you can see that here at the final part here. So that just makes sense about the graph given. It's a displacement time graph for a journey. It says in part A, work out the average velocity for each stage. So they want the velocity for each stage. So stage A, stage B, and then stage C. So that's stage A. The velocity, again, velocity is to do with gradients of this graph. So if we compute the gradient here, again, the change in displacement or change in y, if you want to think of it that way, is 5 meters, and then the time is 20. So the velocity is 5 over 20, and it's positive because it's going up. So it's going up. The line is going up, so the gradient will be positive. And the units are, well, the displacement is in kilometers. Oh, so that should be a kilometer, 5 kilometers. My apologies. So 5 kilometers over 20 seconds. Minutes. Okay, minutes. Those are my units. So that would be 0.25 kilometers per minute. Okay. But they want the units to be in kilometers per hour. So kilometers per hour, by the way, to the -1, this is kilometers per hour. It's the same thing. These two notations are the same thing. In A level, we will be using this notation where we have in a negative power. So remember, anything to the -1 is 1 over that number. So h to the -1 is 1 over h, which is then kilometers divided by h, which is this same notation here. So we will be using this notation, but it means kilometers over hours. Okay. The problem here, though, is if it's kilometers over hours, here we have kilometers over minutes. So what we instead need to do, we can't have 0.25 kilometers per minute. We need kilometers per hour. So 5 kilometers, and then we need to convert 20 minutes into hours. Well, you should know that's a third of an hour. 20 minutes is a third of an hour, right? So that'd be a third h, a third hour, right? So then if we do 5 divided by a third, that'd be 15. So 15 kilometers per hour. And then in this sort of notation, 15 km to the h to the -1, kilometers per hour. Okay, right, so that's the velocity there. And for stage B here, well, actually the velocity, you should recognize it's a flat line. It's completely flat. There's no gradient to it, right? There's no change in displacement, so there's 0 here. So the gradient is 0, so the velocity is 0. So that'd be 0 kilometers per hour. Okay. then for stage B, say the final stage, the final line, the final part of the journey, here. Well, again, the change in displacement, so here, it's going down by 5, so it'd be negative 5 kilometers here, okay? And the time at the end, here, so then the time is 50, and then here, so this is between 60 and 70, so this is actually 65. So we've gone from 50 minutes to 65 minutes, so that'd be 15 minutes there, okay? So that'd be over 15 minutes. Now, obviously we want it in kilometers per hour, so that'd be minus 5 kilometers over, well, 15 minutes. Again, you should know that's a quarter of an hour. So then if we do minus 5 divided by a quarter, we get minus 20. So minus 20 kilometers per hour. Okay, we can use this notation here. And there we are. And again, it makes sense to be a negative 20 because, again, as we can see, the line is going down. Right, it's going down, so it'd be a negative gradient, and so therefore the gradient is the velocity, so the velocity would be negative as well. We want the average velocity of the whole journey, so from the start here to the end here. Then the velocity is going to be the total displacement, or the overall change in displacement from start to finish. So if I jot that down, where are we? So the average velocity is going to be total displacement over total time. And so so the displacement, again from start to finish, well, they've not changed really. Start at 0 displacement and end at 0 displacement. That makes sense because it returns to a starting point, right? So it makes sense overall to be no change in displacement. So it'd be 0 then, right? 0 kilometers over the total time, which probably doesn't really matter to be honest because it's 0. But the total time is actually like 65 minutes, if you can see that. It's not at 70, it's at about 65. So 65 minutes. Which goes to 0, okay? So 0 kilometers per minute. Although, to be honest, you can use any unit you want because it'd be 0 anyway. Okay. And there we are. Okay, so the velocity is 0. But then it says the average speed now, which is going to be a bit different. So the average speed, instead of displacement now, we take distance into account. So total distance over total time across the whole journey. Total time. So then the distance, well, to work out the distance, we can just consider each part in turn. Right, so again we start here and end at point A. So the displacement is 5. That would also be the distance at that between the two. So the distance he walked from the start to A is 5, so 5 kilometers. Then from point A to point B, they've not moved anywhere because it's completely still. Okay, no change in displacement, it's just stood where it was. So no distance travelled there. And then at the end, from B to C, obviously the displacement is negative as it returns, as they walk or move in the negative direction or the opposite direction. But physically, they still walked 5 meters. Okay, so 5 meters, you can see here, 5 kilometers. Sorry, kilometers. So 5 kilometers. They still walked 5 kilometers. The distance is 5 kilometers. So we add on another 5. And the total time, again, is 65 mins. So if we work all this out, so that this will be 10 kilometers. 5 add 0 is 5 add 0 add 5 is 10. So 10 over 65 minutes. So that would be, if we simplify it, 2/13 kilometers per minute. Okay. Now, they didn't specify the units for this, actually, surprisingly. The units for part C, the average speed, it just says for work at the average speed. No units required. They didn't say any units. But if you were to give it in kilometers per hour, well, the 65 minutes has to be in an hour. That one's a bit awkward to convert. What you should know is that 60 minutes is 1 hour. So therefore 1 minute is a 60th of an hour. So then if we want 65 minutes, we do 60, 1/60 times 65, so 65/60 hours. So alternatively, if we did, we can say that it's 10 kilometers over, well, 65 minutes as an hour is 65 divided by 60 of an hour. And then if we work that out, if we simplify this, so if we do 10, so what this, if we break down this nasty fraction, we can do 10 divided by 65/60, okay? That's what I can put in my calculator to simplify this fraction. Nasty fraction, because I've got a fraction in a fraction, right? So if I literally break it down to 10 divided by 65/60, that goes to 120 over 13 kilometers per hour, okay? Or as a number, that would be 9.23 kilometers per hour to 2 decimal places, okay? And that is my average speed there. Okay, so we're going to look at some exercise questions then. So here we are told Sarah leaves home at 10 o'clock, as you can see here, and cycled north in a straight line. The diagram shows displacement time graph. Okay, so it's her journey, okay? Then it says in part A, work out Sarah's velocity between 10 and 11 o'clock. Well, 11 o'clock is here, 10 o'clock is there. So the velocity is just the gradient of the line, okay? So the velocity is the gradient, which is changing displacement over changing time of this line, while the displacement is 12, right? That's 12 kilometers, okay? 12 kilometers. And the time, well, it's from 10 o'clock to 11 o'clock is 1 hour, okay? Doesn't specify the unit, so the velocity is going to be the change in displacement to 12 kilometers over 1 hour. That's the time. So that's simply 12 kilometers per hour, okay? Or 12 kilometers to the h to the minus 1, okay? And so there we are. Okay, and again, it's positive. Make sure you consider the sign. It makes sense to be positive because the line is positive, so it's going up. The gradient will be positive, hence so will the velocity. Now for part, then it says on her return journey. So obviously when she returns, it would be that part. On her return journey, Sarah continues past her home. That makes sense because makes sense to return when she returns home to be back to zero displacement. But if she's going past her home, it would actually be negative, right? Because she's going past it, right, in the negative direction. Anyway, then it says in part B, estimate the time that Sarah passed her home. So what time did she pass her home? Well, again, it's just what I said here. It's going to be here, right, when the displacement goes back to zero. Now, again, you can spot it's not at 1 o'clock. It's a bit awkward. Well, in the middle here, it'd be 12:30, right? So it'd be 12:45, right? If it's between 12:30 and 1 o'clock, it'd be 12:30. 12:45, sorry. 12:45. So the time would be 12:45. Okay, if it's between 12:30 and 3:0, it should be 12:45. Okay, hopefully you can see that, right? Where it crosses displacement to be 0 is 12:45. Right. Then part C, work out Sarah's velocity for each of the last 2 stages of a journey. So the distinct last two stages, the distinct lines, is this line here, and also then this line here. Okay, so that line and then this line here. So firstly let's deal with this line here. So what we call the penultimate, or the second to last part of the journey. So the penultimate part, so the velocity, again the velocity is going to be changing displacement over changing time, or changing y, changing x. It depends how you see it. So again, this line here, the change in displacement, if we start here and end here for this line segment here, well, the displacement starts at 12 here, 12 kilometers, and ends at well, again it doesn't say, but that would be -2, right? Actually no, -3. There it's, that'd be -3. Okay, you have to read off the graph there. So actually, what if from start to end, we start at +12 for displacement, and then -3 at the end. Well, actually, the change in displacement is -15. Okay, and then the time. Well, the time at what was it? At the time here would be 11:30, right? And then in here it's 3 o'clock and 13:00. So from 11:30 till 13, right? That'd be 1.5 hour. So 1.5 hours. Okay, from 11:30 to 13:00, or from 11:30 to 1 o'clock. Be 1.5 hours. Okay, hopefully you can visualize that by reading off the graph. And so therefore, again, the velocity, the displacement, the change of displacement is -15 over time, which is 1.5 hours. Okay, so then -15 divided by 1.5 is -10. So -10 kilometers per hour. Okay, and so there we are. And again, it's negative because the line, right? The line here is going downwards, so it'd be a negative gradient, so a negative velocity. Okay. Okay, now the final part is this little line part here where it goes upwards. So the last part, so the velocity of that last part, again, well, the displacement, so hit from that point here to here at the end, the displacement goes from -3 back to 0, so it'd be +3. And again, the line is going up, so it'd be a positive displacement. Okay, so the velocity would be +3 kilometers, and then the time, well, it's 13:00 to 14:00, so that's just 1 hour. Okay, so 3 kilometers over 1 hour, which is just 3 kilometers per hour. Okay, or properly, if we use the proper notation, 3 kilometers to the h to the -1, which is the same thing. And then part D, finally, it says calculate Sarah's average speed for her entire journey. So the average speed is going to be the total distance over total time. So distance now, not displacement. Okay. So again, the distance, to work that out, let's just consider the individual parts. So again, get rid of all this. The displacement for the first part here is from 0 to 12. So that's a 12 distance, right? They walked 12 kilometers. And then for this second bar here, they've not moved anywhere, right? It's completely still. The displacement does not change, so they've not moved anywhere. So that's 0 kilometers. They've walked. And then for the third part of the journey, this third line here, right? This third line here. Well, the displacement, because it's going downwards, would again be negative. Well, from 12 to 0, then from 0 to -3. Yeah, -3. It'd be 15, right, negative 15, but the distance, well, they still walk 15, right? So 15 kilometers will be the distance, right, despite it going down, because it's distance. And then for the final part, from this point here at -3 displacement to then 0 displacement at the end, well, it's 3. So a further 3 kilometers. And then the total time, well, what's the total time? Right? The total time, well, they start at 10 and then they end at 2. So that is good 4 hours. Right? So from 10:00 to 14:00 is 4 hours. So there we are. The total time is 4 hours. If we calculate all that then, well, 12 and 15 and 3, that'd be 30. So 30 kilometers over 4 hours, which I don't think simplifies, but as a number is 7.5. So 7.5 kilometers per hour. Oh. And there we are. Cool. Okay, we've got this final question here, and we're told that Khalid drives from his home to a hotel. He drives for, now this fraction here, 2.5, okay? 2.5 literally just means 2.5. Well, half is 0.5, so that's 2.5, okay? So 2.5 hours at an average velocity of 60 kilometers per hour. He then stops for lunch before continuing to his hotel, and the diagram shows the journey. Okay, so part A, he wants to work out the displacement of the hotel from Khalid's home. Okay, right. So the displacement of the hotel from Khalid's home. So obviously Khalid, we're told, drives from his home to the hotel. So it starts at home, and then the end point all the way here would be when he arrives at the hotel. Okay. So they want the displacement, but obviously we just read off the graph, but we don't have any scales on it. There's no numbers on the displacement, so we can't work it out actually. We can't just read off the graph here, because, well, is it? So we have to use the information. So we're told he drives for 2.5 hours at an average velocity of 60 kilometers per hour, and then he stops for lunch. So think about it. If he stops, that's going to be this point of time here. That's going to be this line here. That represents when he stops for lunch, which means the first 2.5 hours. So 2.5 is here, right? That's 2.5. I'm told the velocity. I'm actually told the velocity for this part. The velocity is 60. Okay, so if the velocity is 60 kilometers per hour, and also the time is 2.5 hours, which means the displacement is going to be velocity times time. So it's going to be 60 times 2.5. Very similar to speed times time, right? So 60 times 2.5 is 150. So 150 kilometers. So that means at the end here will be 150. There, if you can see it, right? 150 there. So actually what we can do here then is, now that we worked out the displacement when the velocity, or in other words the gradient, is 60 and the time is 2.5 hours, right? The displacement is 150. Now the scale we can work out from this is how many boxes have we gone up to 150 here. 1 box, 2 box, 3 box, 4 box, 5 box, 6 boxes. So what I could say that then 6 boxes sort of on the y-axis, right? 6 boxes represents 150 kilometers. So therefore 1 box is 150 divided by 6, which is 25 kilometers. Okay, so that means each box is 25. So we have like 25, then 50, then 75, then 100, then 125, then 150. Okay, so what I can do here then is to work out this. Right, if I read off the graph at the end here, at the end point here, which is the hotel, it finishes his journey. If we read off the graph, if we compare that, if we start at 150, we go 1.5 boxes up. Okay, so that would mean it'd be 175. The displacement at the end is going to be 150, and then we add 1.5 boxes. Okay, so 1 box is 25. And then a half of 1 box is going to be half of 25, right? And so if we work that out, 150 add 25, add a half of 25 is 187.5 kilometers. Okay, so this is 187.5 here. Okay. Which is the displacement at the end, okay, just by reading off the graph, okay, because each box we go up in, the scale goes up in 25s, as we saw here, okay. So that's just reading off the graph, right. Now, that's part A. Then part B says work out Khalid's average velocity for the whole journey. So part B, the average velocity, again, is going to be the total displacement over total time so literally how far we gone up in the total displacement. We started at 0 at his house, and then we ended at 187.5. So the total displacement from start to finish is 187.5, right? So 187.5 kilometers. And then the time, how much time have we moved overall? Well, we started at 0 and then we ended at this time here. So that is okay. So that's going to be 3 and 3.75, right? Obviously we go up in 0.5s. So then 3, then 3.5, then 3.75 if it's in the middle there. Okay, and in fact I zoom in here just to make it really clear. So again, at the start to the end, as we've seen, the displacement here is 187.5, which is in the middle. So if this is 150, then this will be 175, and then a half of that. Okay, and then the time, again, hopefully you can see clearer now. It's 3 to 3.5 here. And then midway of a box is 3.75. Okay, so we get 3.75 for time at the end here, which means we're dividing the displacement over total time, which is 3.75 hours. Okay, so if we work that out, 187.5 divided by 3.75 is 50. So 50 kilometers per hour, and that is your average velocity. Okay, so that is displacement time graphs. So hopefully you're a bit more comfortable with them, what they mean, and in particular to how you can work out the velocity by taking a gradient, and then how you can work out the speed and the distance and the displacement by considering the individual parts of the journey. So if the graph is going up, that'd be a positive displacement. If the graph is coming down, it'd be a negative, so negative displacement. Okay, that's it for now. I'll see you next time.